on complex number. We are fourth year student in mathematics English program at lZl Rajabhat University. The topic is property of absolute set. In real number, the value of absolute x equal to negative x, which is x less than 0, and x, which is x more than or equal to 0. This is a real number line. We let point A, F, and B. A is negative 3 and B is 2. Distance between FA equal to absolute negative 3 equal to negative or negative 3 equal to 3. Distance between FB equal to absolute 2 equal to 2. And distance between A, B equal to absolute negative 3 minus 2 equal to 5. Distance between BA equal to absolute 2 minus negative 3 equal to 5. So distance between AB and BA must be equal. So next, this is the definition of absolute set. Let set equal to xy or x plus yi. Then absolute set equal to square root of x squared plus y squared. So we get absolute set 1 minus set 2 equal to square of x1 minus x2 plus square of y1 minus y2. So next, we want to prove 6 properties.
Okay, welcome to the property 1. In this property, we will prove that the square of absolute set equals absolute set square equals set times conjugate set. And first, we will find that square of absolute set. And from the definition, we know that absolute set is equals square root x squared plus y squared. So that square of absolute set is equals square of absolute set x squared plus y squared, and we will get the x squared plus y squared. And ILS in this equation is equation 1. And the second, we will find that the absolute set square. And from definition again, we know that set is equals x plus yi. And so that set square is equal x plus yi times x plus yi. And in this equation, I use the utility property, and we will get the x squared plus 2xyi plus square of yi. And in this point, square of yi is equal y squared times I squared, and we know that I squared equals negative 1. So that square of yi is either negative y squared. And now we know that square of yi is equal negative y squared. And next we will reform it. In this equation, we will get the x squared minus y squared plus 2xyi. And the next we will write to the order pair. We can write the order pair x squared minus y squared and 2xy. Okay, now we know that what is the set square, but we want to find the absolute set square. So that we take the absolute in the set square. We get the square root square of x squared minus y squared plus square of 2xy. And we use the utility property, we can get the square root square of x squared minus 2x squared y squared plus square of y squared and plus 4x squared y squared. And the next we can get the square root square of x squared plus 2x squared y squared and plus square of y squared. And in this equation, is either perfect square. We can change to this form. It is a square root square of x squared plus y squared. And the last we can get the x squared plus y squared. And unless this equation is equation 2. And the last, we will find the z times conjugate z. We know already z is equal x plus yi. So that conjugate z is equal x minus yi. So x times conjugate z is equal x plus yi times x minus yi. And we will get the x squared plus y squared. And unless this equation is equation 3. So now we get the equation 1, equation 2, and equation 3 are equal. Hence the square root of the absolute z equal the absolute z squared as equal z times conjugate z.
And this is property number 2. We will prove that absolute z equals to absolute negative z equals to absolute conjugate z. We will let z equals to x plus yi equals to order pair xy. And conjugate z equals to x minus yi equals to order pair x minus y. Negative z equals to negative of x plus yi. So it's equals to negative z, negative x minus yi equals to order pair negative x, negative y. So that absolute z equals to square root of x squared plus y squared. And absolute conjugate z equals to square root of x squared plus negative y squared equals to square root of x squared plus y squared. And absolute of negative z equals to square root of negative x squared plus negative y squared equal to square root of x squared plus y squared. Hence, absolute z equals to absolute conjugate z equals to absolute negative z.
Okay, for the third property is absolute z equal to 0 if and only if real z equal to 0 and imaginary z equal to 0. Before we will prove, we must know definition of real z and imaginary z. If z is a complex number, you can write a complex number in z equal to order pair xy or z equal to x plus yi. So we call x is a real z, and we call y is a imaginary z. So since absolute z equal to 0, and we know already absolute z is a square root of x squared plus y squared equal to 0. So we take a square in both sides, we get x squared plus y squared equal to 0 squared. And 0 squared equal to 0, we get this equation. Since x squared plus y squared equal to 0, if and only if x equal to 0 and y equal to 0. Let's see back in the definition. If x equal to 0, we get real z equal to 0 and y equal to 0, imaginary z equal to 0. So we get absolute z equal to 0 if and only if real z equal to 0 and imaginary z equal to 0.
For the property 4, we will prove that absolute z1 minus z2 equal to absolute z2 minus z1. Now we know that absolute z1 minus z2 equal to square of x1 minus x2 plus square of y1 minus y2 equal to square root x1 square minus 2x1 x2 plus x2 square plus y1 square minus 2y1 y2 plus y2 square and we use commutative property of multiplication and addition, we get that square root x2 square minus 2x2 x1 plus x1 square plus y2 square minus 2y2 y1 plus y1 square equal to square root square of x2 minus x1 plus square of y2 minus y1 and equal to absolute z2 minus z1. So absolute z1 minus z2 equal to absolute z2 minus z1.
For the definition 5, we will prove absolute z1 times z2 equal to absolute z1 times absolute z2. From the definition, we know already absolute z square equal to z times conjugate z. Proof absolute z1 times z2 square equal to z1 times z2 times conjugate z1 times z2. We will take out the bracket. We get z1 times z2 times conjugate z1 times conjugate z2. We regroup in the simple form. We get z1 times conjugate z1 times z2 conjugate z2. From the definition, we get absolute z1 square times absolute z2 square. Then we get square of absolute z1 times absolute z2. So absolute z1 times z2 equal to absolute z1 times absolute z2.
For me, the last property is property 6. We will prove absolute z1 over z2 equal to absolute z1 over absolute z2. Since absolute z square equal to z times conjugate z. Since absolute z1 over z2 square equal to z1 over z2 times conjugate z1 over z2. And we take bracket out z1 over z2 times conjugate z1 over conjugate z2. We get absolute z1 square over absolute z2 square. And we reform equation absolute z1 over absolute z2 square. Hence, absolute z1 over z2 equal to absolute z1 over absolute z2.
Thank you ขอบคุณค่ะ